to the demo video of Spring 2025 with us at Design Lab with our group DPMIC. So let's do a self-introduction first. My name is Francis.
My name is Sean.
I'm Emily. I'm Isha.
And Horan.
It's Yang.
Okay, this is a brief introduction of our project. We designed a digital PID controlled DC buck converter. My name is Hongxin, by the way. We have two motivations. First of all, the traditional analog control converters often struggle to fine-tune the control loop. So in the nowadays advanced buck converters, I think digital control is also widely used. And another thing is that if the buck converter works in the DCM, there will be reversed current, which will impact the overall efficiency. So we added another module to shut off this reversed current to improve the efficiency in the DCM. And the figure 1 here shows our post buck converter block diagram. We have 2.5 input voltage. We have 2 switches. They are all 2.5 I/O devices in TSMC 65nm process library. The LCR output stage is placed off chip, and because they all have a very large value, the output can swing from 0.9 to 2 volt, and with a ripple which is 50 millivolt, and the inductor current ripple is roughly 100 milliamp. And this buck converter can support the maximum load current 500 milliamp with the switching frequency 1 megahertz. And because our control loop is actually in the digital domain, we need an ADC here to convert this feedback analog voltage into digital signal. And the PID controller will use this digital signal to calculate the duty cycle with the help of 3 16-bit PID coefficients Ki, Kp, and Kd. We use the scan chain to scan in those data, and also some other control bits. Another block is the digital PWM generation. It will generate the PWM waveform using the duty cycle number. And the overall system actually work at 64 megahertz, generated by a ring oscillator clock gen. And we use the dead time generation to generate 2 non-overlapping square waves to separately control the MP and Mn, because we want to just avoid the shoot-through current. And another thing is that the core voltage is 1 volt, so we need some level shifters to shift the voltage potential from 1 to 2.5. And in order to drive the very large gate capacitance, we need some buffers to minimize the path delay. And the last one is the ZCD, or zero crossing detection. The basic idea is when the MN is turned on and there is reversed current, Vx should be greater than 0. So we just sense the Vx voltage and using some logic gates to turn off the NMOS switch and short the inductor to release this power. And that's how we shut off the reversed current to improve the overall efficiency. And the table 1 here shows our design specs. Most of them are covered before. So other things include our ADC resolution, which is 3-bit. This is actually a 3-bit flash ADC. We use flash topology because of its high speed. And the die size here is 2 by 1 millimeter square. The packaging we use is QFP64L. Okay, this page shows our layout, the chip layout packaging. This is our floor plan. We have the top level I/O pads, test module, DUT. DUT include the digital top, analog top. And the chip level layout here is strictly following the floor plan. And the die photo here is similar to our chip level layout. This one is the packaging. Again, it's the QFP64L. It's 10 by 10 millimeter square. And these two, as you can see here, are our chips. This one is with the typical package, and this is the glass package, which is very, very nice. Okay, so lastly, I want to briefly introduce our chip test. This is our test station. We have the laptop to scan the program, the scan chain. We use the MATLAB to scan in those data into the chip through an FPGA here. And this is our FPGA, and this is the PCB that we designed. The demonstration will be introduced later. And this is the test results. The phi and phi B signals are the clock signal of the flip-flops in the scan chain. And this clock is actually, its frequency is divided by 1000. So here the clock frequency is 64 kilohertz. So the real chip clock frequency is 64 megahertz. That is what we expect. And these two are VX and VOUT. VX is the switching node voltage. So when the PMOS is turned on, it will be some high voltage, and when the NMOS is turned on, it will be near zero. And the VOUT here is roughly 1.9 volt, with the ripple is 50 millivolt, and you can see the ripple clearly. So above all is the brief introduction of our design.
This is one of our chips under microscope. It's sealed with glass so we can see what's inside. So as for the demo board, we designed our 4-layer PCB in Autumn Designer. And we have 5 different schematics sheets shown here, including the top sheet, the buck converter circuit, the microcontroller circuit, and finally the microcontroller peripherals. We then laid out our board. The top and bottom layers are both signal layers, and the middle layers are power and ground plane. So this is a view of our board in Autumn Designer. We then assembled our board using both reflow oven and hand soldering. So this is our demo setup, and this is our demo PCB here. It's powered by 5 volt through a Type-C connector, and this is our buck converter chip shown here. And before the chip can run, we'll use MATLAB to scan in the scan chain signals to our chip. This includes the PID coefficients and the clock generation settings. So all of those values are going to be loaded into the chip through the FPGA shown here. And right now, I'm going to click Run. So we can see that the scan outputs match the scanning bits perfectly, and we can also see the test pass message shown here. So this means that the scan chain signals have been loaded into the chip successfully. So right now our chip is outputting roughly 1.8 volt, and for the demo we will use this OLED screen as our display. It runs at 3.3 volt, and it communicates with this STM32 microcontroller using I2C communication protocol. We will also monitor the real-time current and voltage data provided by our chip so that we can see how it performs under different load situations. As of right now, the program has been loaded into the microcontroller through this ST-Link connector, so we can start the demo right now. So we have 3 different demo sections here, and for the first part, we will use our chip to power this STM32 microcontroller directly at 1.8 volt, and we will run a snake game on it. So on the display, we can see the real-time voltage and current that our chip is providing. So in the following sections, we will use our chip to power the 6x5 LED array. And first, we will show some numbers. So we can see as the numbers changing, the current also changes. And after that, we will show some simple symbols and some effects. So as the LED turns on one by one, the current gradually ramps up. After that, we have a blinking heart. And finally, a raindrop animation. So yeah, that's the end of our demo, and we can see that our chip performs reliably under real scenarios. At the end, we want to thank everyone who helped us throughout this project, and we also want to express our gratitude to Apple for their generous sponsorship. Lastly, thank you for watching this video.